Okay, let's get started, please. Let's get started, please. Please put away your phones, electronic devices. You're all. Okay, thank you. Yeah. Okay. Have you ever heard about? The experiment where they have, there's a psychology experiment where they have, they say, okay, everybody, we're going to show you a video of a basketball game, okay, and we want you to count how many passes are made in this basketball game. Okay, so everybody starts watching. They show the video. Everybody starts watching. There's people passing to each other, and everybody's counting like 1 pass, 2 pass, 3 pass. Okay, and then at the end of the video, they say, how many of you saw the gorilla? How many of you saw the gorilla? Right? And everybody says, what are you talking about? There was no gorilla. There was no gorilla. And then they rewind the tape, and then they show it again. And through the middle of the basketball game, there walks a man in a gorilla suit. Right? He's like, walks through the middle, and nobody sees him. Right? Nobody has seen him because they've all focused on the passing. Okay. So this is sort of how I feel about people reading their phone and teaching. I'm the man in the gorilla suit. Right? I'm up here, and you think somehow that you are seeing things, but in fact, your focus is so on this that you don't even see what the man in the gorilla suit that's in front of you. It's impossible for the human brain to concentrate well on 2 things. You can only concentrate on 1 thing. If you have your phone out, you're not going to hear anything. You're not going to see what's happening right in front of you. So I think yeah. So that's keep that in mind. The human brain can only concentrate on one thing well, right? No matter what you think. Okay. Okay. So we are going to do section 7.7 first, and then maybe come back to section 7.6. Okay. 7.6 is a lot of physics. I'm not sure how important that is to cover for you guys, unless you're going into physics. So we're going to do. However, this stuff is important. So differential equations. Differential equations. Okay, so let me start off with a definition. A first order differential equation is an equation of the form y prime equals f of xy. Okay. So the derivative is some function of x and y. The derivative is some function of x and y. So for example, somebody tells you that the derivative is actually negative 2 over xy plus 4x. Okay, so this is some statement about the rate of change of the thing that you're interested in. Okay. Or, for example, somebody tells you that y prime is y minus 4x over x minus y, x minus y. Or another example, saying that y prime equals negative x over y e to the negative x. Okay, so these are examples of differential equations, right? And you use them to model things in reality. Another definition. A solution of a differential equation. A solution of a differential equation is a differentiable function that satisfies the equation on some interval, Okay, so for example, suppose I say f of x is x squared plus 1 over x squared. Okay, f of x is x squared plus 1 over x squared. Okay, then what if I take the derivative of that, f prime, that's going to be 2x plus negative 2 over x cubed, right? That is the same thing as negative 2 over x times x squared plus 1 over x squared plus 4x. What are you thinking? I don't understand. Okay, yeah. If you need to use your phone that much, just leave class. Yeah, I don't want to see it. Yeah. I understand that you're addicted. You're all. I understand that this new generation, you're all addicted. Okay, but I don't want to see it in class. Yeah, that's just. First, you're not going to learn anything. Second, it's rude. It's rude. Okay. Okay. So look, here's this function, right? You take its derivative, and look what happens. Y prime actually equals negative 2 over xy plus 4x, right? Right. So this thing here, this is a solution to the first differential equation, right? This is an example of a solution. Okay. Okay. So what we're going to be dealing with today for the first part, I think, is something called separable differential equations. Separable differential equations. So so you have this differential equation, y prime equals f of xy. If f of xy equals g of x, h of y, we say the equation is separable. Okay. The equation is separable. Okay. So for example, this one here, you notice we can break it into two functions, right? 1 over y and negative x over e to the negative x. Right? So it's the product of two functions, one function of y and one function of x. Okay. So this last equation is a separable equation. Okay. Okay. And the trick to doing separable equations, so how one tries to solve separable equations. Right? You have dy dx is g of x times h of y, right? And then what you do is you separate the variables, okay? You separate the variables. So you say dy over hy equals g of x dx. Okay, or maybe let me write it like this. 1 over h of y dy equals g of x dx, and then you integrate both sides. Okay, so you integrate one side with respect to y, you integrate the other side with respect to x, and hopefully you can figure out what y is. Hopefully you can figure out what y is. So that's the general method of that's one way that people try to solve separable differential equations. Let me do the simplest example. Okay, so here is the prototypical example. Okay. Okay, so P of t, we're going to call this, P of t is going to denote the number of a population with a certain disease at time t. Okay, so you have your population, and there's a certain number of people have a disease. Okay, and the disease is spreading. The disease is spreading, and your assumption is that P prime is proportional to P of t. Okay, so the rate of change, right, is proportional to the number of people who have it. Right? The more people have it, the faster. The more people have the disease, the faster it's going to happen. The faster the disease is spreading. And the fewer people have it, the slower it's spreading. Okay, so the rate of change, the rate of increase of the disease is proportional to the number of people who have the disease. Okay, so in other words, P prime of t is equal to some constant times P of t for some k bigger than 0. Right, so this is your assumption, and then the question is, what can we say? What can we say about p? About this function P of t. Okay, so we're going to do separation of variables. dp dt, right? P prime t is k times p. Yes, of course. Yeah. dp dt is kp, right? And we do the separation of variables. We see that dp over p is k dt, and we integrate both sides. Okay. Everyone see that? Right? This is the separation of variables trick. You move everything involving p to one side, you move everything involving the other variable to the other side. Okay? Okay, well, what's the integral of dp over p? Right, it's going to be natural log, right? Natural log of p. And then what's the integral of this? Well, this is just going to be kt plus c. Right? Natural log of p is kt plus c. What does that tell you? Well, first off, let me get rid of the absolute values. So population is positive. It's bigger than 0. So we can get rid of the absolute values. Okay. You get natural log of p is kt plus c. That tells you that p is e to the kt plus c, right? Some constant. Right? Because that's how the natural log works, right? Natural log of something is this means that p is e to that, right? Okay, and this is the same thing as e to the kt times e to the c, right? Which I'm going to rewrite as c prime e to the kt. So call this thing c prime. Okay. So, what does it say? It says that if this is true, if p prime t is proportional to p, then the spread of the disease is exponential. The spread of the disease is exponential. In other words, the disease is going to spread very quickly. Okay, if this is true. If this assumption is true. So maybe this assumption is true. If it is, then the disease is going to spread throughout the population extremely fast. Okay. Okay. So let's see. Yeah. So turns out that no, okay, I'm going to do this. Okay, so let me do another example. So a less simple example. Okay, so you have a bunch of mice and you have a bunch of owls. Okay, mice and owls. Okay. And P of t is the mouse population. It's the number of mice that are in the forest, say. So let's say that dp dt is 1/2 p of t minus 450. Okay. So what this is saying is that the rate of change of the mouse population is proportional to the population, right? So if we didn't have this thing, right, what would this say? This would say dp dt is proportional, right, is some number times c of p of t, and our mouse population would grow exponentially. Okay, so this is, in this world, the mouse future is glorious, right? You're going to have mice overrunning the world eventually. Right? There'll be exponential growth for the mouse population. Okay, but there's owls. Okay, and in every unit of time, the owls kill a certain number of the mice. Okay. Okay, so you're wondering, well, what's going to happen? What's going to happen to the mouse population, right? Okay. So, okay, why don't you try and solve it? Use separation of variables and see what you get. See what can you figure out about P of t. Okay. Use separation of variables on this and see what happens. Okay, talk to each other and see what you're doing. Be patient. Talk with also public. Okay, anybody like to give it a try? You've got dp dt equals p of t minus 900 over 2. Okay. So what do? Well, you say, okay, this is going to be dp over pt minus 900 equals 2 dt. Right, what do you get? What do you get? Huh?
No.
Wonky, what is it? Are you lost?
I didn't. When you first write the definition of this one, I don't quite understand, but I know you take the differentiation of each other, and I don't know why you want to do it.
Why?
I don't quite understand what, like, after you did this, what will.
Okay, well let's go on and see what happens. Okay, so right, so but you're okay with this to here, right? You know, I mean, you just I mean, it's sort of illegal, but you do it anyway. You move this thing down here, you move this thing over there. Right? You multiply through by dt, you divide by p of t minus 900. Okay.
What is dp?
Hmm?
What is dp?
What is dp? That's a good question. Just pretend that you don't have to answer that question. Okay. But you can think of it as the thing that you're integrating against. The thing that you're integrating against. Okay, so for example, if I'm integrating x against dx, right, then this is going to be this, from 0 to 1, right, this is going to be x squared over 2 between 0 and 1, right? Okay, but if I'm integrating x against dy between 0 and 1,
I don't know.
right, okay, so I'm integrating, that y is my variable, and x is just a constant then. Okay, so then what this is actually the integral of this. Okay, and what this turns into is x, y gets evaluated between 0 and 1, and you set it with x.
Wait, for the first one,
Yeah.
I know the x equal x, but for the second one.
dx doesn't equal x, right? dx is sort of telling you what your variable is, right? What your variable of integration is, right? You're taking x and you're integrating against dx, right? And you get this. Okay. Okay. Well, how about the second thing? Does this make sense? If I integrate, this is it's okay to be confused about this because it's a little strange. If I integrate, say, 1 against dy between 0 and 1, right? What am I going to get? I'm going to get 1. I'm going to get y between 0 and 1, right? That's going to be 1 minus 0. That's just 1, right? Okay. Now, if I integrate some number, dy, right? I have a constant here, right? This constant is a between 0 and 1, right? I integrate that thing, and I'm gonna get a, right? That's okay, right? Okay. If I integrate x between 0 and 1, right? This x is just some constant, right? It's a height, x. So what am I going to get? I can pull out the x. I get the integral from 0 to 1 of dy. I get x times 1. That's x, right? Right? You're integrating against y here. I'm not integrating against x, right? Here, if I'm integrating against x, as x goes from 0 to 1, then I'm integrating this, right? Right. Then I'm integrating this, right? Right. And so I'm going to get the integral from 0 to x dx. That's x squared over 2, 0, 1. That turns out to be a half, right? Right. You see that this and this are entirely different things, right? Here I'm integrating against x, or maybe another, yeah, one. You have something to say? No? Okay. Maybe another way to say it is in terms of infinitesimals. Okay? You say, look, what I'm doing here is I'm taking x and I'm multiplying it by some infinitesimal width dx, right? I take the height, which is x, right? The height here is x. I multiply by infinitesimal dx, and I keep on adding those guys together, and eventually I get the area of the triangle, which is 1/2. Okay. Over here, what am I doing? Over here, right? I have some number x, right? And here is the y-axis, right? And what I'm doing here is I take x times dy. That gives me the area of this rectangle, and then it gives me an area of these rectangles. I add them all together, and then I get x. Okay. Do you see that? I hope it's becoming clearer that these two things, integral of x dx between 0 and 1 and integral of x dy between 0 and 1 are completely different. Okay. So one way of thinking about this dx is an infinitesimal. Okay. It's some sort of infinitesimal length, right? And when I have this thing here, I move the infinitesimal to the other side, right? And now I'm going to integrate. Right? I have this 1 over p of t minus 900 against dp, right? So maybe I'll just call it p. P minus 100 dp. And over here, I have 2 against dt. Right? Yeah.
Should be 1/2.
Oh yes, thank you. If you don't like that 1b, you can avoid it. You could say, okay, here's how you can avoid it. So this is, I think your calculus teacher would like this. You can avoid it. You could say, I'm going to write this as p prime. Okay, is p of t minus 900 over 2. Okay, and then I'm going to integrate everything. No. I'm going to move. So this will do the same thing. Divide like that. Okay. And then I'm going to integrate against dt both sides. Okay. This will give you this will result in the same answer if you do it this way or if you do it this way. Okay, but maybe this way is more satisfying. I think this way actually is more satisfying. If you don't like to multiply through by infinitesimals because you feel that that's illegal, right? And some people don't. Don't worry about it. Don't worry about it. You don't have to understand infinitesimals. It's a shorthand for this. Okay. One way you can either believe that there actually are things as infinitesimals, or just say what you're doing is just notation for this. Okay. So if you like, don't worry. Just keep everything as functions of t. Integrate with respect to t on both sides.
Like for example, that one you have divide, but like one you have that's one
So dividing is okay, right? Dividing is okay?
yeah, how do you add divide according to
How do you what?
add your variable by you add t?
So all we're saying is that take the antiderivative of both sides, right? Right. If take the antiderivative of both sides, take the indefinite integral of both sides, right? If this is equal to this, then the indefinite integral is going to be equal to the indefinite integral, right? If I have two functions, f of t is g of t, then certainly the indefinite integral of the left-hand side is going to be the indefinite integral of the right-hand side because they're the same function, right? So I've got two functions. I have two functions that are the same. Here they are, right? This guy equals that guy, and so I know that their indefinite integrals are going to be the same, right? It's just like if I have a equals b, I'm allowed to say that f of a is going to be equal to f of b because a and b are the same, right? Or if a equals b, certainly a squared equals b squared, right? Because a and b are the same, right? This and this are the same. I'm sorry. This and this are the same, so their indefinite integrals are going to be the same. Okay. Just we can talk more later if you like. Okay. But in any case, you end up with this thing here, right? Okay, you end up with this thing here, and you integrate it. What do you get? Well, you end up with the natural log of p minus 900, right, equals 1/2 t plus c, right? Okay. Then you say, okay, then I know that p minus 900 equals e to the 1/2 t times e to the c, which I'm going to write as e to the 1/2 c plus. Okay. Okay. Right. So if p is bigger than 900, right? If p is bigger than 900, then what we have is p of t minus 900 equals c e to the 1/2 t, right?